Voilà, très bien. Voilà, donc I'm very pleased to introduce Georges Gontier, who works in the Microsoft Research Lab in Cambridge and in the INRIA Microsoft Research Joint Center in Saclay, where he leads the mathematical components team. So as Cédric Villani explained already, Georges is famous for completing a machine-checked proof of the four-color theorem in 2005. And more recently, in 2012, he announced that he completed with his team a machine-checked proof of the Fate-Thompson theorem. This is a great achievement. So Georges was recently called in Le Monde theorem hacker. So we are delighted to have him here to explain his work and his achievements.
Oh, thank you. No. Okay. Okay, so I was going to introduce myself, but since both Cédric and Paul-Henri did it brilliantly, everybody knows what I'm about now. I would just mention that after this stunt with the four-color theorem, I decided that maybe I would do some more mainstream mathematics. Like the four-color theorem is interesting graph theory, but graph theory isn't something that goes into the everyday work of mathematics, and finite group theory and algebra are, and it's also a little more useful subject. So that was the point in going into the order of theorem. So here's the statement of the theorem. As was mentioned, it's a nice theorem to prove because it has a very short statement, just one line, and a very interesting proof that was actually rather controversial for, from what I gather, about 20 years. It took about 20 years to iron out all of the kinks and bugs from the proof. No one ever doubted the theorem, but the proof was a bit subject for debate. We did manage to actually explain all of those details and iron out a few other kinks in order to get this through a computer proof-checking software. So below you have the check theorem, which actually looks, except for the use of symbols, looks pretty much like the theorem on the top. And indeed, it is a simple theorem to state because you only need 54 lines from bare logic in order to state the theorem. However, you need about 45,000 lines to prove the theorem, which isn't so bad if you consider that that maps to 250 pages of graduate text. And to correct Cédric a little, it actually only took us 2 years really to prove the theorem. But there was an extra 4 years of background work. And I guess the way of visualizing this is that the proof of the theorem occupies about a book and a half to fit the 250 pages. So that's the revised, improved proof, which is still 250 pages long. Apparently you can't compress the proof any shorter. But in order to formalize this, you really have to formalize not just the two books, but actually a bit of a bookshelf, because you really need to teach the computer how to do, well, basically all full undergraduate algebra curriculum and some graduate group theory to go with it. The computer graph of that is something like that, which is meant to just look daunting. Of course, you can't read anything. But if you detail what's going on in this bit, the very bottom part, the little comma at the bottom, is what was needed to formalize the four-color theorem. So very, very basic logic. The lofty tower on the top is the actual proof, which is pretty linear. And that was one of the reasons for selecting it. And the big mess in the middle is kind of the fertile ground from which the tree could grow. And that's basically where that undergraduate curriculum, algebra curriculum is. And if you zoom into that bit, you can see that each of these little blobs is actually basically an undergraduate course. And if you actually look at the file, it starts with a syllabus that describes what this is about. And that particular file there gives you basic finite group theory. Just to give you a flavor of the proof, just to show you that it's somewhat complicated, it's divided in two parts. Local analysis, where you look at the shape of the subgroups of the groups of odd order that you're considering. And because you're doing the proof by induction, you know lots of things about the subgroups, but nothing about the whole group, and you're trying to infer information from the combination of the two. The analysis ends up with this conclusion, which is there in line 3, that says that most of these subgroups have a specific shape called the Frobenius group. And there are lots of background facts in order to get there, and there are lots of caveats that make all the complexity of this proof. There are many exceptions to this. In particular, instead of having this easy two-layer structure, you can have a three-layer structure. And then the proof shifts gear completely. So that's why there's a second book, because in revising the proof, everything couldn't be done in one go. You had to have really two different people working on the two separate parts of the proof. That's also why the original theorem has two authors. So the second part uses character theory, which is basically taking your groups and reinterpreting them as groups of matrices with complex coefficients. And this brings in the whole range of basic linear algebra and geometry, because you get to use properties of Euclidean spaces and to write down norm inequalities. And this particular norm inequality here is kind of the key of the proof, because it's actually impossible. So it's and that inequality would hold if all of the groups, if the structure on the previous slide was exact and held everywhere. So it's a structure that forces you into exceptions, and then you get a final exception which is basically a description of a finite field. And then you have to shift gears again and use Galois theory in order to complete the proof. So pretty much everything in undergraduate linear algebra or algebra goes into this proof. So the plan for proving this was to do a first layer that has just the very basics of arithmetic and algebra. And then from this start building up group theory, and then combine this with matrices to talk about representations, which was interpreting groups as matrices. Then in parallel to that, develop character theory. Then using the extra properties of representations you get from character theory, derive essentially the maximal group structure, so local analysis, and then get the inequalities and prove the Auer theorem. I got branded as basically some sort of Napoleon by my colleagues when I showed this plan. But it actually worked out pretty well. So here's one of the interesting theorems in the proof. That's the theorem that establishes and characterizes the exceptions to the general Frobenius structure. And this is how the theorem looks like once digitized, formalized on the computer. And I'll get back to these two things, but I just want you to know that they're about the same size, and so we're talking the right language, and that's really the important thing to get, and what we worked on the most, trying to be able to get the computer to understand the language that is used in algebra textbooks, as opposed to some kind of coding one could come up with in logic. So, one very basic example of this is getting the algebraic notations done properly, so that all of these formulas we can write and get not only something like LaTeX that prints a pretty picture, but actually write a formula that means something, so that we can write something that looks like LaTeX, but actually describes the Leibniz formula for the determinant, and that lets us prove things about the determinant. And if you look at this definition from a purely logical point of view, it's missing a lot of information. And it's by using I'm not really a mathematician, I'm really more of a computer scientist, and it's really computer science techniques that are used here to understand how the gaps are being filled. And the proof that this works is, well, basically in the doing. So let's take a basic mathematical proof using matrices and this type of notation. So proving that matrix product commutes under trace. And the proof is just expanding definitions, then commuting summations, then commuting the coefficients. And so it's a very simple proof. And what's nice is that it's a very simple proof, even coded on the computer. That's really all the text of the proof. So it's a 4-line proof on the page, and it's a 4-line proof on the computer. And if you can go through all the steps of the proof with the Coq system, and it'll tell you at each point what you know and what you need to show. So for example, this is your basic context that says you have matrices A and B, and you want to show that they commute under trace. The first step you're going to do is to show this expansion formula, and that's just a 1-line proof. And you're going to want to actually apply the expansion formula twice. And here I've just annotated the first proof to tell it that you should regeneralize the matrices A and B along with their sizes. So we can just use this this rule twice and commute the summations, and then we just need to apply commutativity under summation, and we're done. So very simple proof, and very simple to do. So what was used to do this? What does Coq provide us that let us do this? Well, the most important thing is the notion of type. So that's how you get extra meaning from typing in some kind of expression. You assign to an expression a meaning that says what object it is, but it also gets some categories. So basically, anytime you say something, you're saying two things at once. And that's really the trick hidden in understanding mathematics. And Coq makes this the very principle of its logic. So it actually uses types to encode not only data objects, but also proofs and propositions. It has this, and because it uses, has data types as objects, it can compute with them. And that's what's used in in a major way in the proof of the four-color theorem. But it is also used here to compute the meaning of things like summations and compute subgroups or quotient groups, for example. The thing on the bottom is the extra fluff you get from having these types, which is that you can omit a lot of information and use an algorithm to reconstruct it. So information you've omitted, instead of being just something that is reconstructed by a convention, is something that, which might be a little imprecise, is reconstructed by a precise algorithm. If you strip away all of this extra stuff, you still have a usable logic. And indeed, that's the Otter theorem. So I mentioned you only needed 50 lines. So those are the 50 lines that get you to a bare bones statement of the Otter theorem, not using any extra fluff. I mean, the only extra fluff you're using is this page that gives you basic arithmetic. However, you're getting a theorem that's a lot less usable than the form I showed you initially. because, well, it doesn't have the ability of understanding what a general notion of cardinality or a general notion of group. It's just specialized to proving, to stating the theorem. You couldn't possibly show the theorem with this theory. And you can get even fancier notation, so things that you would think as completely ill-defined, like, for example, defining a sum of subspaces and then stating later that this sum of subspaces is direct. Doesn't mean anything in logic, because the sum of subspaces is going to be equal to some space, say the total space in this case. So saying that the total space is direct doesn't mean anything. As it turns out, there's enough flexibility in the type inference to actually make sense of such a statement. So that's about basic algebra. So how does it apply to group theory? Well, in group theory, you have a web of notions to deal with, like subgroup, normalizer, normal subgroup, and so on. And on top of these, you have operations on group sets, subsets of groups. And you have operations that happen on elements. And the key idea in understanding how this actually needs to be formalized is to understand that there's a distinction between groups as objects, which are really sets, and groups as types. And not if you understand this distinction, you realize that really group theory is a misnomer. It should be called subgroup theory. Because basically, that's all. That's what it means. We have the very nature of objects is going to tell you how to multiply them, and what you're interested in studying when you're proving something like the Euler theorem is proving properties of certain subgroups. So groups are sets. And in Coq, you explain this very easily by saying, okay, you have this notion of a group type, which provides you with multiplication. Then you can define the property of being closed under product, which defines what a group set is. And then you can define an object that's a set that satisfies this closure property. And that gives you a way of building group theory by having a set of interfaces that provide various operations, and having for groups things that are both objects, the sets, and interfaces which provide this extra property of being closed. So you have this little diagram where each of these blocks lets you connect theorems together. And that's really the key to building larger proof, is being able to connect theorems together, even when they don't fit exactly. So that was the key to proving this this theorem here, or actually stating the theorem. And the proof is, I guess, is in the doing. Not only that you can write something that kind of looks like the LaTeX source for that theorem, because of course you could just take the LaTeX source, but also that you can actually explain to a rigorous checking system exactly how the proof works. And the proof is rather involved, so this is kind of half of it. And the computer proof is just as involved, and I see that on this projector you can hardly see it, but it's just built of the very same pieces we saw on the simple example. And just as in the simple example, you can use the proof assistant to assist you in understanding the proof. So you can run the proof up to a given point, and the system will tell you exactly what you know at this point. And this is a complicated proof that proceeds by generalization and induction. So you not only do you have to prove a 30-line statement, but you also have a 20-line induction hypothesis, which appears on the right here. And if you're reading the text, you have to come up with the induction hypothesis basically in your head. And it's very easy to get those induction hypotheses wrong. And indeed, in the revised proof that has been revised over 30 years, there are actually a couple of induction hypotheses that are clearly wrong. And so it's very nice to have a system that actually understands what you're typing into it, and that will tell you when you've done a misstep. So in this case, we're about on par with, I'd say, with the original text. It's probably the formal proof is twice the size of the, say, the text input for that text proof. There are cases, though, where the theorem prover, the formal theorem prover, is actually better than the manual theorem prover. And those are the cases where we can actually exploit the ability of the system to understand what computation is. One clear example of this is when you have things that are defined by recurrences. Because then you, in a manual proof, you need to expand the recurrence every time you use it. On a computer system, you tell once and for all that these objects are defined by recurrence, and then it knows automatically how to use the recurrence. So in this case, you have these two pages that are captured by about a page of user input. Another place where this works out really well is when you have really messy algebra, because there's actually an algorithm underpinning the simplifications that are done here and expressed with clever use of braces over and under the lines. And so again, in a formal proof, you can write down the principles that underpin those simplifications. So you can give general definitions for the groups you're simplifying. Not groups in the sense of group theory, but just subsequences of symbols. And then explain how these simplifications are linked one on the other. And so you can, again, write down a page of formal text that formalizes 2 pages of normal text. You can even do better when really there's an algorithm, but you can't. But the algorithm is basically run inside the text. This happens once in the. This happens all the time in the proof of the four-color theorem. It happens once in the proof of the Veit-Thomson theorem, where you have to show a certain combinatorial property of a matrix of vectors with 3 orthogonal components. And basically what this proof is doing is it's running over all the possibilities of, or what it's doing rather implicitly, if you go down to the details, running over the possible ways you could have, a choice of components you might have to make sure that you only get a simple arrangement where you have one common component for each line, one common component for each column, and one for each cell. So in this case, there's actually an algorithm, a very simple decision procedure that is being run here, this looking at all possible combination. And it's very easy to program this decision procedure in a language because you have a programming language. And it's very easy to show that your program is correct. And so in this case, you can write down a proof that has only the top-level analysis. And every time the proof is the text does something very hand-waving, like saying, "Oh, well, it looks like some other case," you can actually say, "Yeah, it is this other case," and have something that checks that it's the other case. So you can have your. If you're not happy with the logic Coq gives you, you can write your own logic instead, and in this case, it works particularly well. So perhaps to be honest, one case where it doesn't work so well, so this is the the final stand, the final piece of the proof we did. And I think we're about for a factor of 4 here because, well, this was just the last mile and we weren't going to factor the proof anymore. We just wanted to be over, it to be over. Okay, I have 5 minutes to explain a few things we got out of this. So the computer scientists that do verification are always tested on how many bugs they find. Now, you could expect that if you're looking at a revised proof that has been analyzed for 30 years by all the specialists in group theory, you aren't going to find very many. But there's one anecdote that I like to recount, which is the wandering typo bug, because it's actually quite... I thought it was an urban legend before I did this proof. So the proof is in 2 books, and at the end of the first book you have a recap that summarizes the principal conclusions of local analysis. So one of the important conclusions is hidden in this theorem 15.7, which has 5 different conclusions, and in the second part of the 5th conclusion, it has this bit of a statement. And then in the recap, this bit, the bottom of square has the line C has basically a property that comes from this theorem. If you look closely, that part of the property has an M there, and there's an H in the original text. So, silly typo, pretty much impossible to spot because the proof just says, well, look at the other theorem. And when you flip pages, an M just looks just like an H, and you're quick to forget that it's not the same group. But the interesting thing is that the second book is very cautious, and so not only does the first book have a summary of the episode, the second book has a summary of the previous episode, where it explains all of the conclusions of the first book it needs, because it was about 5 years between the 2 publications. And so in its list, it goes on and describes the property, and as you can see here, the M is still there. So the typo was carried over from one book to the other, and the only saving grace is that the second book is wrong and doesn't need that assumption. Otherwise, I'd have been in real trouble, and I actually have gone and write to people that actually know something about group theory in order to fix, again, the proof of the outer theorem. So even in the best of circumstances, errors happen. And yes, to some extent they happened because there were a lot of minor errors in that theorem 15.7. So I guess the other thing we got from this was a kind of natural byproduct of the fact we were working in Coq. Coq has Coq's internal logic is more restrictive than the logic that's generally used in mathematics, or more precise. It's a constructive logic. So it doesn't allow you to do natively proofs by contradiction. Every proof has to be, everything you have to prove has to be a material implication. However, anytime you do something combinatorial, like when you have some kind of decision procedure, then there's no difference between working by contradiction and working constructively. And so you can encapsulate classical reasoning and be very precise as to when you're using classical reasoning. If you were forced to use just constructive logic, you wouldn't be able to translate this proof as it is. But you can carefully encapsulate all the classical bits and eliminate classical reasoning at the proper points. There's one caveat. This works really fine for proofs. It doesn't work for constructions. So unfortunately, if you're going to do character theory, you need the complex numbers. So we had a first plan for doing this, because we now need the construction of, well, not complex numbers, because those are real, contain real numbers within our construction. So algebraics are fine. So the plan A was to construct the real algebraics, and there's a fairly obvious way of doing this, although it requires significant work, and that was basically the topic of Cyril Scoen's PhD thesis. And then you need to prove a fundamental theorem of algebra, but you can't use the usual proof. So you need to use a special proof that uses matrix encodings. And then I came up with Plan B, after Cyril had defended, which is a much better way of doing this, which is to use a general construction for getting countable algebraic closures. And my colleagues that wanted to use a library to prove things about elliptic curves were very happy to get algebraic closures for their finite fields as well. And then you can take the standard proof of the fundamental theorem of algebra and interpret it constructively within this setting. So you get a little bit of new math, not as much as I would have hoped, I guess. So I'm going to conclude with this, which is a bit of a repetition of what Pierre-Louis said. What you get from these things, you get certification. So you know that proofs are correct, so you know that proofs that involve computers are not getting lost in the translation when you move from the textbook statements to the computer statements, as could have happened in the four-color proof. And I guess Tom will be talking a bit about his experience with the Kepler conjecture, or his theorem. Or you can get certification of complex proofs, and as we've seen, well, even years and years of revisions still let little errors slip in, and you will get lucky and have inconsequential errors. You might also get unlucky. Then there's the part that Pierre-Louis mentioned about inspiration. These systems are wonderful tools for exploring logic, exploring dependencies. The whole business of refactoring proofs, revising proofs and making them simpler is helped tremendously by having everything about the proof in the system. And I'd like to insist on the middle part, which Pierre-Louis hasn't mentioned, but I think is a very important part of these systems. They're excellent tools for collaboration. All of this project wasn't just my work. There were about 10 people, most of which are in this room. And I'm not going to put up the list, but they'll hopefully they'll forgive me for this. None of them were group theorists. None of them were really mathematicians. Some of them didn't really have much of a formal mathematical training. But they all could contribute because having an ironclad platform on which to work made it safe for them to do so. And also, the platform would explain to them theorems that, on the face of it, they didn't understand. So once the notation had been explained to the system can explain the notation to new users. It works beautifully. And I guess that's the end of my speech. Thank you.
Are there any questions in the room?
Hello. I think you mentioned something. I just wanted for you to say a few more words about it. About group as a type and group as a set. Am I right to hear in these words something from Church type theory, where set is defined as a pair consisting of a type and a function from this type to the type of propositions. Is it what a set is?
Well, a set is in this case, sets actually have a specific data representations because they're finite sets. So they're list of booleans if you go down to it. But the point is that sets are mathematical objects. So they're objects you can manipulate. Whereas types are just are basically tags, are classifications of individuals, or perhaps to put it differently, types are sets are used in traditional mathematics in both as a classification system and as objects in their own right. And if you take general sets as a classification system, it's kind of not as useful as it could be, because a classification has to have some restriction to be useful, especially in an automated setting. In normal set theory, any object can belong to an object can belong to any number of sets. And so it's rather unsafe to extrapolate properties of an object based on which sets it belongs to. The point of type theory is that an object belongs to a single type. And so it's much safer to use types as a basis for inferring missing information, supplementing missing information.
Okay, so we have time for another question.
So in the some of the parts that you presented, it looked from the outside a bit like tech writing from very superficial point of view. How far can we go to the end in the direction of the end user for being mathematician friendly in the approach?
So also there are a number of systems that let you do rendering. Oops, sorry. I'm not that concerned about this, for one thing, because the reason it looks like tech is because it's ASCII, and the reason it's ASCII is because the keyboards are ASCII, whereas text on a page is something that is typeset and doesn't change. Text on a computer is something that you tend to change a lot. And so it's easier to change something for which you have the keyboard. You can, you can have intermediate points where, for example, you add Greek characters to your alphabet, so you can have the alpha letter instead of ALPHA. For the purpose, at least for the purposes of going as far as the Euler theorem, it's not really an issue.
But I was.
May I try to maybe add something to this? Just sorry, George.
Mm-hmm.
So the first time I heard George speak, I couldn't understand how that relates to what we would consider Euler theorem. Now I understand it almost completely. It was about a year and a half which had to pass between these 2 points. So in terms of how well it can be adapted to a mathematician, I don't know. But in terms of how long it takes for a mathematician to get adapted to this, it's not too bad. I mean, it's
no, but maybe, Vladimir, you are so slow, you know. Okay, but I was not thinking so much in terms of the letters or something like this, but for instance, things like we use for any element in this thing, etc. Rather, we like to put bits of sentences inside the theorems, and it must not be too difficult to have something that translates this kind of partly automatically.
Yes, it's a bit technically difficult to do within the tools that Coq give you. There are other systems that are somewhat better at this, Mizar especially. And if you come to the first workshop, you'll see talks that will present this beautifully. I have to plug my own workshop.
Okay, so let's thank Georges.